Okay, class. So for our Monday class, what we did, we started the last module of this course, and we discussed how to quantify, at first, how to identify different types of losses, and then how to quantify those losses. So we figured out we have in total 2 different types of losses, major and minor. Major losses was due to friction, and the minor losses was due to any type of irregularities on the way to the flow, right? That's what we figured out. So for today, what we will do, we will try to do some mathematical problems for head loss. Now for any pipe flow problems, we need, just like any other fluid mechanics phenomena, we need to, like, 3 conservations should be like satisfied: mass, energy, and momentum. So mass is the one which is, the another name is continuity equation. Energy equation, you already know that. And the last one is the momentum conservation. So the good thing here, we we usually don't work with the momentum equation for pipe flow unless we need to do work with any force or something. So you will not see that much use of momentum equation here, but that doesn't mean that momentum equation is not conserved. It just conserved, but since we are not working with the force here, you will not see that we are doing all the calculations. Okay, so most of the time we will use energy equation and the continuity equation. Okay, now for today's class, make sure you have this one handy, this one. Open your class example 23 and make sure you have this one also, the one I just, you have already one, but this one is, you can keep that with the class example 23 so that you will not be lost, like from where you got all the values. Okay, so what we will do today, we will try to find head loss for a setup. Now, the reason I gave you this one, like this table, usually for head loss, we can have broadly 3 different types of problems. For type 1, everything is given, we just need to calculate head loss. For type 2, we need to calculate the discharge. And for type 3, which is the design problem, we need to calculate the, or determine the size of the pipe. So we will do one problem from each type. So today we will do one problem, which is class example 23. So let's work on that. And while we will work on that, we will come back to this table frequently. So make sure you have that table handy. And if you can't hear me, just stop me. I'll repeat again. Okay, so who will read the class example 23A? Yes, that.
Valve that leads to flows out to 65 millimeters gas pipe with velocity 2 meters per second. The pressure of the pipe is the density of water is 916 grams per meter cubed.
This is the viscosity, kinematic viscosity. Yes.
Viscosity of water is -6 meters per second.
Thank you very much. So we have a section of pipe here from A to C, and we need to calculate the pressure at A. Now, they didn't say anything about ignore minor losses. So we need to check whether we need to calculate the minor losses or not. Okay, so that's what we will do. So let's write down all the given values first, and then we will decide how to work on the unknowns. Okay, so the given values. So the very first one is what? The diameter is given, right? So it's 65 millimeter. We will convert that into meter. From now on, we will always write down what is the material of pipe, because that will help us to identify the friction loss or major head loss also. Okay. So the pipe material, cast iron pipe. Okay, and we know the velocity, which is 2 meters per second. Determine the pressure in the pipe at A. We know the density, which is 996 kg per meter cube. We also know the viscosity, 0.8 to the power 6 per second. Okay, so that is one thing. Now we need to check what are the sources for minor losses we have here. Okay, so let's do that. Here, what are the sources of minor losses you can think of in this whole setup? This pipe is below the ground level. You can see this is the ground, and there is a bend, there is a valve, there is no change in diameter, so there is no contraction, no expansion, which is good. So so we have two sources of minor losses here. One is one bend and one valve here. Okay, so I will just write down the name here because we will need that at some point. So what type of valve we have here? Fully open globe valve, right? Okay, and we have 90-degree bend. Okay, so we have this, and now we need to calculate. Okay, can anyone calculate L over D? What is that ratio? L over D here for this problem. Total L is what for this problem? 10. Okay, and D is 65 millimeter, right? So you need to convert that into meter and tell me what is the L over D. Say it again. 153.8. Okay, so that is actually less than 1,000. And if you can remember, we said that if the L over D ratio is greater than 1,000, we usually ignore the minor losses. But here you can see it's way higher than 1,000, way lower than 1,000, right? So we need to calculate the minor losses here. So that's what we will do. Now find, we need to calculate the pressure at A, P, A. That's what we need to find. Okay. Now, whenever we need to calculate pressure, velocity, the energy equation is the one where we can find pressure and velocity, all of these together, right? So that's what we will do. And as I said multiple times, usually we always use the energy equation in between 2 points. Literally any 2 points we can choose, but it will be wiser if we chose some points where some value is 0. Just think about point C, the water is coming to the atmosphere or something like that. So you can consider this, the pressure at C is 0, right? So we can choose 2 points. And since we need to find the pressure at A, let's choose, let's apply the energy equation in between A and C. So that will give us at least 1 0, and at the same time, that will help us to find the unknown. Okay, so let's do that. Apply energy equation in between A and C. So P, A, gamma pump, turbine should be C. Head loss, right? Okay. Now the next step is to identify what values we already know and what values we can cancel. The first thing, in between A and C, do we have any pump or turbine? We don't have any pump or turbine in between A and C. So these two are 0. Now the piece, the bottom here, this one is open to atmosphere. So PC will be what? 0. Okay. Now the same Q is going through all the pipes and there is no change in diameter. No, we have only one inlet, one outlet, which is A and C. So do you think the velocity at A and C will be different or they will be same? They will be same because same Q is going. There is no change in diameter. So VA equals to VC equals to 2 meter per second, right? So that means you can cancel these two terms here. Now one more thing here about ZA and ZC, right? So they already gave you the datum at C. So can you tell me what will be the ZC? It will be 0. And what about ZA? So it's 6. That means finally we have PA over gamma 6 equals to head loss, right? That's what we have here. And since we are trying to find PA, so let's rearrange this equation. It's creating so much problem today. Okay, so that is the equation for PA, right? Now here we can find the gamma value because density is given, so we can calculate the gamma value, but we don't know the head loss value, right? So we need to calculate the head loss right now, and that is the next step. Okay, so let's do that. Everyone's done up to this point. Okay. So the next step is determination of so we know head loss is actually the summation of major and minor loss, right? Minor loss or losses if we have multiple sources here. So we'll write down this way. For major loss, we always use the Darcy-Weisbach equation, which is F L over D square over 2G. And for minor losses, we use KL square over 2G. I used the summation because we may have multiple sources of minor losses. So that's why the summation of KL. Okay.
What's that one called?
The
First one's called Darcy.
Darcy-Weisbach equation. This one.
And the second for the minor.
For minor one, there is no name. It's just the equation. So now what we will do, we will again try to identify what values we already know and which one we don't know. Do we know F at this point, friction factor F? It's not given, and at this point, I don't know how to calculate that. So I will just stop F as like here. What is the length in between A and C? Because that's where I applied the energy equation, right? What is the total length? 6 plus 4, which is 10. The diameter is 65. We know the velocity, which is 2 square. And what will be the G value here? 9.81. Now summation of KL, I don't know at this point, but I will find that. This one. So if you look at the given values, we had two sources for minor losses, right? One was a fully open globe valve and another one was 90-degree bends, right? So what you can do, you can go to this, like this packet, and from page number 3, we can have different types of KL values. We just need to find out which one we will use. So I will I will use table 10.1. Okay, you have that in your packet. So what type of valve we have here? We have fully open globe valve. So that is one. And we also have 90-degree bend. Now, here, if you look at in this table, they have two 90-degree elbows. Since they didn't mention anything, whether it's a long sweep elbow or something, usually long sweep means it's very wide. We can't see that here and they didn't mention anything. So we will check the conservative route and we'll check the highest one or higher one, which is the 90-degree elbow short radius, which is 0.9. Okay, so that's what we will use here. You can go back to the very first one and just write down that KL is 10 and KL is 0.9, table 10.1. Okay. So write down that. And then I'll come back here. I'll write down 10 plus 0.9. Now give me this number without the F because I don't know what is F. And this number also.
31.36.
31.36. Okay. What about the minor losses?
1.1.
Calculate that again. That should be something around 2.22, something like that. Make sure you square the velocity. What number you got?
2.22.
Yeah, that sounds right. Okay, So that is the head loss expression. Now we still don't know friction factor F. So we need to find friction factor. And for this one, like what are the steps we should follow? You can come back to this table and can you tell me what type of problem we are dealing with? Type 1, type 2, or type 3 here? We are dealing with type 1. Everything is given. We need to calculate the pressure drop. Now, for any type, like whether type 1, type 2, type 3, for calculating the friction factor, at first we need to calculate the flow type, whether it's laminar or turbulent. Because for laminar, it's easy. It's 64 over Reynolds number. For turbulent, we need to do something else. So that is the step here. Find the Reynolds number and determine the type of the flow. So that's what we will do now, okay? So let's do that. Determination of F. To identify the flow type, Reynolds number is the only way which will tell us whether it's laminar or turbulent. Okay, so that's what we will use. So V was 2, V was 65 over 1000. And the viscosity was what? 0.8, 10 to the power 6. Now give me the number in terms of 10 to the power something. You should get a very high number. Yeah, give me 10 into 10 to the power something. Okay, all of you got something similar to that. Now this number is way higher than 2300. That was the critical Reynolds number, which will determine whether the flow is laminar or turbulent. So that means the flow is turbulent. Now again, go back to this table and tell me for turbulent flow, how can we find the friction factor for type 1? Okay, so for turbulent flow, Moody's diagram is the one, which one we have to use for calculating or determining the friction factor F. Okay, so I will write down that. Now everyone open your Moody's diagram, the one I gave you today. And this step to find the F from Moody's diagram, it's the most important part for rest of the class in this semester, because next 4 lessons, that's what we will do. We will just find friction factor F from Moody's diagram in different situations. So it's important to understand how we can do that. Okay. Now, all of you should have this one, right? If you look at this plot again, we are trying to find friction factor F, right? So we need to know Reynolds number and epsilon over D. We already have the Reynolds number, so we need to calculate epsilon over D, right? Okay, so epsilon is dependent on the material type. What type of material here we saw for the pipe? The cast iron. So I will go back to this table. You have that on top of the movies diagram here. For cast iron, we have what? This one, right? So epsilon is 0.26 millimeter. And we need to calculate epsilon over D. Since this one is in millimeter, I will use 65 so that a unit get cancelled. And this number gives me in terms of decimal, not to 10 to the power something. What number you got for this one? 0.004. Okay. Now what I will do, I will go back to the given values and I will just write down these on that table also so that you will have everything on the same table. Okay. So 0.004. I will go back to the very first one here. Cast iron. Epsilon is 0.26 millimeter. I don't need to write down epsilon over D. If you have space, you can write down that. But if you don't have space, that is fine. Okay, now we have epsilon over D. We have Reynolds number. Now our next task is to find the friction factor F. Okay. So for this part, we'll spend as much time as we need, but we need to make sure that we get that. So all of you have this one. Okay. Now, if you look at this part, it's epsilon over D, and every value here, it's yes. The one you have, I gave you today, that is the black and white copy, but in this copy, like this page, you have the color one, I guess. Oh no, you always had the black and white one. I had the color one. Okay, so for this one, if you look at epsilon over D, everything is in decimal format. That's why I asked you to give me the number in decimal format. And if you look at the Reynolds number here, everything is in 10 to the power something format. So that is the reason I asked you to do in 10 to the power something format. Now, we have two steps here. The very first one is we need to find out epsilon over D equals to 0.004. Okay, so can you see that line here somewhere? It's here, right? 0.004. Okay, sometimes we may not have the line. Just think about 0.003. We don't have the line here. In that case, we just need to draw a parallel line. But for this one, we already have that. So what you can do, highlight this line or make a thick line on top of that, just like this way. Okay, 0.004. So do that, everyone. Make sure you do that and write down the steps maybe so that it will be helpful before the test. Once you are done, the next task is to draw a line for Reynolds number. Okay, so what Reynolds number you got for this problem? 1.63 10 to the power 5, right? Okay, this is the most common part where you will do the mistake for homework and the test. It says that 1.65 10 to the power 5, right? So at first find 10 to the power 5 line, this one. This is the 1 into 10 to the power 5, 10 to the power 5, that line. And then move to the right direction, okay? And draw a vertical line just like that, 1.6. I got 1.625, that's what I have used. So, but obviously that is not the most correct one here. Draw a line. Now, what should be the next step? Now you can imagine a little bit, how can you find the friction factor? What should be the next step now? you will find the, yes, that is correct. So you will find the crossing line here, and you will draw horizontal line just like this way. Okay. So I got 0.029. That doesn't mean you will get the same. As long as it's close to 0.029, that should be fine. Now I will wait few more minutes just to make sure that all of you got the friction factor test. So what you will do, everyone please find that, and once you are done, just let me know. I will then check your friction factor test. Okay? You got that? Make sure you highlight your Moody's diagram for like these two lines and everything, so that before the test, when you know that how to do it. Just highlight the line so that otherwise before test will be so long. Those who found F, you can to let the question because that is on that.
So that's all of that. What's the, oh.
Yeah, yes, yes. Yeah. Yeah. Class, just to make sure we all got that, how to find the friction factor F, because that's the thing we will do for rest of the semester, like next 5 classes. That's what we will do all the time. So at first, epsilon over D, then Reynolds number, and then friction factor. It can be other way also, like you can draw the Reynolds number first and epsilon over D. The main thing is you will need these two to get the friction factor. Okay, so maybe you won't get 0.029 exactly, use whatever you got. So what I will do, I will just go back to that equation 1 here, and I will use 31.36 0.029 plus 2.22. So what is the total head loss here? 2.13? 3.13? Okay. 3.13 meter, right? Okay. One interesting thing here. Can you give me this number? What is that number? 0.9 something maybe. Now, if you look at this problem, the minor loss is actually higher than the major loss, right? Here, that's because it's a very short pipe, only 10 meter. And within 10 meter, we have a band valve. That's why we are getting higher minor losses here. Okay, so 3.13. Now, again, I'll go back to here. 3.13 minus 6. I don't know gamma, but density was given, which is 996, 9.1. What number you got here? Negative? Yes, that should be the one. Okay, so that should be the answer for this one. The reason you are getting negative because section A is just a cut section from a whole system. It's not the beginning of a system. So since you're like taking a section from the whole setup, that's why it's the negative pressure inside that pipe. That means it's suctioning water from the other side. Okay. Okay. So before we move to the part B, please let me know that you got how to find the friction factor F. Yes.
Did you say that's negative because it's a very small portion?
No, I said that it's negative because you took that small portion from a big setup. That means it's not the starting point. It's like if you have that type of setup, like this camera setup or something like that, if you just take a half of that at some point, like this is the setup here. Okay. Okay. So are we good up to this? Yes.
The minor loss this equation because the things that
L over D.
Yeah.
That is one reason. Yes. And another reason is they didn't say ignore minor losses. So if they don't say ignore minor losses, I need to check whether I should consider minor loss or not.
So you've got a number less than 1,000, so you consider it.
Yes. Yes. But for this problem, if they said, even if we got less than 1,000 and they said that ignore minor losses, in that case, we wouldn't consider the minor losses. But they didn't say anything. That's because from that calculation, you saw that minor loss actually higher than the major loss. So you can't actually ignore that. So you need to calculate that. But yeah, that's the way. You will always calculate L over D and then decide whether you consider the loss or not. Okay. Okay. So let's work with part B. Part B is very much simpler than part A, and we will take lots of numbers from part A. So let's work with part B. Can anyone read the part B very quickly?
The same setup, heavy oil is flowing instead of water. determine the total head loss within the
Viscosity of oil,
viscosity of oil to be
something.
0.12.
Okay, thank you. So for this part, instead of water, if we had heavy oil, what would be the head loss? That's what we need to find. So what we will do from part 23A, total head loss was 31 point, what was that, 23? $31.36. F plus 2.22, right? We already know that. Now, again, the only thing we don't know is the friction factor F. And just like 23.1, we need to decide whether the flow is laminar or turbulent. So that's what we will do. Flow type, Reynolds number, VD. You may ask, ma'am, why we are again calculating the flow type. The reason we are using a different fluid here, so flow type can be changed. So velocity is 2 again. The diameter is 65 over 1,000. And the viscosity is 0.12, 10 to the power. 3. Now what is the number you got? And 1083 is actually less than 2300. That means this time the flow is laminar, it's not turbulent anymore, right? And if you have a laminar flow, can you go back to this table and tell me how can you find the friction factor? For type 1, for laminar flow, it's easier to calculate the Reynolds number because that is the only thing which affects the frictional loss. So what we will do for laminar flow, friction factor is 64 over 1083. What number you got? So for friction factor, what number you got? 0.06. Okay. And now what is the head loss you got? Five point 4.1. And the unit will be meter, right? Because it's a head. Now, if you go back to your class example 23A, what was the loss for water? 3 point something, right? And for the oil with the same setup, now the head loss is 4.1 only because of that high viscosity, right? And if you look at the total pipe length, the total pipe length is 10 meters. Within that 10 meters, you are getting a head loss of 4 meters. That means there's a huge head loss is happening within that system. mainly because of the minor losses, and for when it's oil, it's due to friction also. Okay. So I will stop here for today's class. For Friday, we will do 2 more class examples. I think one you already have, which is class example 24. I will give you one more. And maybe then we'll discuss, we will go through the test 3 solution also. Okay. Thank you, class, and start working on your homework. If you have any question, let me know. Just give me